So at the end of the last lecture, we ended by discussing epimerization, racemization through oxazoles of oxazolones of amino acids. So what we were noting was that if you had an activated ester of any kind, like any HBTU, HBTU, HCTU, HATU, DIC, EDC, acid chlorides, whatever, doesn't matter. If you had activated esters, and you use standard coupling conditions to attach a new amino acid, then definitely will epimerize. So I'm using the term epimerize rather than racemize, because racemate would mean that you're making all chiral centers in the molecule flip or mix, and we're not. We're really just dealing with one. If there are other chiral centers in the molecule, like something over here, we're not going to affect this. We're not going to touch that. We're only going to touch the one that is directly adjacent to the center, as we were discussing. So I'm interconverting, but the right term I should be using is epimerize, which means flipping a single stereocenter. Anyways, so what this basically does is this means that you can't make peptides this way because you'd never be able to keep the stereochemistry of your amino acids intact. And so what this means effectively so we can't build them from the N terminus to the C terminus because we can't make this bond very effectively that way. So we can avoid this whole issue if we make sure that this oxygen here is not nucleophilic. It can't react. Because if we can prevent that from happening, if we can prevent that formation of that ring, then we're good. Now, there's nothing we can do. It's an amide bond. You're stuck with it because that's what's on a peptide. So instead, what we do, and I'd say this is almost universal, we build peptide C to N. So we always, and this is really confusing, so we always write a peptide sequence from nitrogen to carbon left to right. We always build it backwards. So if we're building a peptide, normally what we want is we want to have the C terminus protected.
Dr. Trent, you drawing something? Because we don't have.
I'm not sharing my screen, am I?
No.
That is going to really make things difficult. I'm sorry that, okay, somebody pointed that out to me earlier. I'm sorry, I'm really sorry. Now, how do I do this? Oh, there it is, I've hidden it down here. Yeah, of course I'm drawing something. I'm really sorry, guys. Okay, otherwise this is just, wow, okay, wow, that was special. Okay, so all my circling and arrows do not make a lot of sense. So I'm gonna erase all my circles. Oh shit, I I don't know if it might be easier just to start from scratch. Okay. So when we were in last class, thanks for us.
Sorry, I thought maybe you want to explain something at
No, I
first
always do it
and
visually.
then
It's really hard to me to
I'm
do this.
sorry.
No, that's fine. Thank you. You saved a lot of this because I would have kept going on thinking I'm sharing my screen. And if nobody's saying anything, I'm going to assume I'm sharing my screen. Okay, what we were talking about was the fact last class that it's really messy. Let's see if we can use the laser pointer. That if we want to build, if we have a peptide like this guy here, like a growing peptide, we're drawing it from nitrogen to carbon as we should. There is a leaving group on the carboxylic acid, so it's an activated ester of some sort. Any of the things that we talked about last class will be fine. We have the nitrogen protected as we should, and we have a peptide bond in it. And then we have two stereocenters. If we try and couple an amino acid using standard coupling conditions, which is we use the activated ester in the presence of a weak base like diisopropylethylamine, and Zoom just told me that people can now share and see my screen. Thank you very much, Zoom. I wish you had told me that people can't see my screen. Then and then we're trying to couple an amino acid. The problem we're going to have from last class is that under these conditions, this oxygen here is going to be nucleophilic, and it's going to make that oxazolone. I can never pronounce that word. And you will epimerize this center here, as we discussed last class. So you can limit that by using special conditions and playing with it, but you can never reduce it to zero. So for a given set of conditions, it's tolerable for a single reaction. But as we just saw when we were discussing how yields drop massively as you increase the step count, even for high yielding reactions, this becomes unviable if you're trying to make anything of any length. So what this means is essentially we cannot build peptides from nitrogen to carbon. We can't do this because we will face this epimerization challenge, and it's a fundamental limitation of the structure of peptides. So what we need to do is we need to build peptides the other way. And what I was good, and before Ronaz correctly interrupted me to say, "What the hell are you doing? You're not sharing your screen." The point of this is that it's really confusing because we always write peptides from nitrogen to carbon. It just that's the convention. So if I write a sequence of amino acids, I mean the nitrogen terminus is on the far left, the carbon terminus is on the far right. If I write a protein sequence, that's exactly the convention we use. N terminus at the beginning, C terminus at the end. It's just how we do it. I don't know why. It was a completely arbitrary decision. But that was decided before we realized how we had to make the damn things. And we have to make them from C to N. So the sequence we build is the opposite of the sequence that we write them in. So let's take a look at why this works. So let's say I have an amino acid. And now I couple that with an activated ester. Sorry, I'll be consistent. I'm not defining which one. It can be benzotriazoles or carbodiamides. It doesn't matter. Sorry, I'm drawing the rare, not unnatural amino acids with that stereochemistry I had. And what we do is we tend to use this functional group called a carbamate. So what I'm doing here is I'm protecting the nitrogen. And I would say 99% of N, maybe clearer, maybe alpha nitrogen protecting groups, peptide synthesis, are carbamates. We're going to see three major ones. This one is the tert-butyl, and it's called that's a really shitty bracket. This is called a Bach group. And so I'm just going to abbreviate it as Bach going forward. And what we have here now is the added oxygen. You'd think it would actually maybe increase the nucleophilicity of this oxygen, but it doesn't. It actually decreases it and allows more electron density to stay on the nitrogen. And so because of that, you decrease the tendency of this thing to ring close onto that to make the ring. So you end up not making the ring. So because we have this carbamate instead of an amide, we make this whole molecule less reactive, which is good. So now it doesn't make the ring, now it can't epimerize. And so what this means is we can't build them from C to N because we get this problem, but we don't run into the problem when we go this way. Because if we make the product of this, so let's say we treat those DIPEA, we get our product. I'm just going to change the protecting group on a carboxylic acid just so that I can be real. So I don't need to lie. So we get that. Now if I deprotect that, and we'll talk about how to do this in a moment when we talk about the different deprotecting groups, but I'm going to use trifluoroacetic acid. It's just a very acidic version of acetic acid. Then the Bach group is going to fall off. It's not going to touch anything else in the molecule. Then what we can do is we can treat this with another carboxylic acid, another amino acid, some coupling agent, and the base. And now we're not going to get that epimerization, right? Because we're going to make the activated ester here. It doesn't matter what's going on with here. Here's our amide bond. This is what was giving us trouble last time. But that amide bond isn't 5 atoms away from this carbon. Now we have this carbamate. And we don't need to worry about the carbamate epimerizing this center. So again, we now add the next amino acid. And so we've added valine now. So we're able to snap on one amino acid after another to make our molecule. And then we just deprotect again, we reprotect, we deprotect again, we reprotect, we deprotect again, we reprotect, and eventually we can make a peptide of whatever length you want. You're only limited by how good are your yields and how patient you are and what you need, I guess. Repeat ad nauseum. Okay. So what's really, really important, and what we notice here, is we don't ever really need to protect the carboxylic acid side. We need it at this terminus, but we don't need to protect it for the individual amino acids that we're adding. So let's just take a short digression into the three protecting groups we're going to need to worry about. Unlike sugars, there's not a ton of them. There are three for the amines. There are protecting groups for the side chains as well. I think I've left that as an exercise in one of the assignments. And I think the best way to do that is you look up a commercial supplier of amino acids and you see what they're using to protect their side chains and why they do that. So there are three. There's Bach, which we've just seen. Bach is this carbamate. You can remove this under two conditions. You can use either acid or heat. The acid, it comes off in any pretty strong acid. The general conditions are 1-to-1 TFA to dichloromethane. So you're 50% TFA in a solvent. You can take it off using 1 molar HCl as well. The problem is 1 molar HCl does a lot of other things as well to your molecule. TFA is very selective. It tends to only remove the Bach group. If you're using standard peptide stuff, HCl can cause you some grief. And so mechanistically what's happening here is we're able to attack the H plus from the TFA. We'll walk around underneath it and come back up on the other side with the product. So you get the protonated carbonyl. That shouldn't be too much of a surprise. You can draw a resonance structure of that. And now you take advantage of the fact that you actually do make a carbocation because it can be trapped. Kind of wish you didn't, but and then what normally happens is the TFA counterion removes a proton and you make isoprene gas plus, guess I can And I'll draw with the geometry I was using. And the isoprene is a gas. So the trifluoroacetic acid you're keeping track doesn't get consumed as catalytic. We do use a lot of it to really push the reaction forward and make sure we have a nice acidic environment. But the TFA doesn't, just regenerates. Your only byproduct is a gas which evaporates away. So Bock groups are very nice because there's no impurities you need to remove. Like you do the reaction, remove the solvent. So you can do it either that way, or heat it to 100 greater than 150 degrees Celsius in solvent. And this just happens spontaneously with basically the isoprene falling off, making a carbocation, and then a liberated carboxylic acid from your amino acid, deprotonating it to make isoprene. So Bock groups are not thermally stable above 150, and you can also remove them under acid. Then this is normally done at like room temperature, the top one. But it does work at 0 degrees as well. You need to be careful. So this is a very, very, very flexible leaving group. The second one we see is called the CBZ group. What is this? We'll draw the same. Also a carbamate because everything is a carbamate. So it's a benzoyl carbamate. And it's not like the benzoyl group that we saw in the sugars, the BZ group, was kind of benzoic acid. This isn't benzoic acid, right? This is benzyl alcohol attached to a carbamate, just to keep things complicated and abbreviations all being confusing. So it stands for carboxybenzoyl alcohol because this is like the carboxy part. So we've got a carboxy attached to benzyl alcohol. So the way we take this off, unsurprisingly, whenever you see a benzyl group like this, is hydrogen, palladium on carbon. Normally in some sort of protic solvent, methanol, normally in a combination with something like DMF, some solvent that really solubilizes peptides really well. The protic solvent's needed to give you an H+, it just helps move things around. I'm going to say nobody fully understands how hydrogenations work, but we can kind of draw a mechanism. So roughly speaking, what happens with any, and I don't think we've done this, what happens with any benzyl hydrogenation is we're making toluene. So what we have basically, I guess I'll draw it down here, is we have like this palladium surface, lots of palladiums. We have hydrogen gas, and the hydrogen kind of attacks the palladium surface. And I think there's two ways you can draw this, and I'm not convinced by either of them. I think the truth is somewhere in the middle. We have the hydrogen gas kind of absorbed onto the surface, and what that does is it weakens the hydrogen-hydrogen bond. I think it's also okay for you to draw it something like this. That's fine too. So we have, and I'm not trying to keep track of what the charge is doing on palladium. It's a metal complex. The charges are all dispersed. But either way, you're making weak bonds. And palladium hydrogen bonds are not strong. But you can catalytically crack open that hydrogen-hydrogen bond. So what then happens is if you have benzyl group coming in close. This is true for benzyl groups as well that we were seeing with the sugar stuff. We essentially, I would accept almost any sets of arrows on this. I think the ones I like the most are something like that. I was up late watching, well, for me, late watching Canada, Mexico, enjoying a good game, with Canada actually not looking completely incompetent for maybe the first time in our soccer history. So what we've done here, right, is we've added these, I'm going to put the hydrogens in a different color. We've added the two hydrogens onto the carbon and onto the oxygen. Well, this thing here is just toluene. So that's common solvent. Again, note that we really don't have like a hazardous byproduct or something. It's something we can easily remove just by, reducing pressure and evaporating it off. And on the other side, like, well, I don't have an amino acid. I've got this weird ass thingy. So this is not a stable functional group. Bunch of ways to think about it, but it just doesn't want to exist like this. There's nothing anchoring it, and it's really easy for us to draw. I'm just gonna do this stepwise. Something like that. Then we get a proton transfer. That is completely illegible. Is the likely one to happen? No. It only needs to happen once, because as soon as that happens, you create gas. And whenever you can create gas, reactions are basically irreversible. So we generate an equivalent of carbon dioxide. So you get this primary carbonate, this carbonate without anything attached to it. I don't even know what it's called. Carbamic acid, maybe. It doesn't exist. You can't make that molecule because it falls apart as soon as you make it into what I've just shown here. Because as soon as you can make this thing, you lose carbon dioxide. It just is not a thing. So what we've done is we've used hydrogen gas to break a carbon-oxygen bond, using palladium to add hydrogen to both the carbon and the oxygen. And then we expose this carbamic acid kind of thing, and it just decomposes immediately into the amine and carbon dioxide. So that's CBZ. And so we have hydrogen sensitive. No, we're really not creative, right? For the carbohydrates, we had acid, hydrogen, base. And so our next one is base. This is the most important of the lot. It gets used the most. It's the Fmoc group. And it's just weird. I don't really understand the chemistry of this. really hard if I draw it wrong. It's very, very specific. It's a very, very balanced acid-base reaction. So this is Fmoc. It stands for fluorenyl, not fluorine the atom, but fluorenyl. It's spelled exactly the same way, except there's an E instead of an I. Methyl, that's the M. Fluorenyl methyl carbamate. Oh, carbamate kind of thing. So what takes it off is secondary amines. By far the most common one is piperidine, which is this guy. So what's cool about this, primary amines doesn't affect it. Tertiary amines don't affect it. Strong bases like sodium hydride, it's immune. You need a secondary amine. And so what that tells me is the mechanism I'm going to show you is not right, but it's the one we use because there's no reason why some of those other ones won't work. But they don't. But no one knows what the possible other mechanism could be for this. So if we treat this with, and normally it's like 20% of this, 80% DMF. So use a very concentrated solution of your base. Yeah, I'm gonna draw the arrow all the way around. So we deprotonate that hydrogen. Why? Any idea for why that hydrogen is so acidic? So they just used a weak base to deprotonate a carbon hydrogen bond. It's not trivial.
It's tertiary.
Tertiary is one reason, yeah. So, well, tertiary would actually be bad, right? Because tertiary will give you a C minus at tertiary center, which would be destabilizing.
So it's because it can does this resonance when it's deprotonated.
Yeah, and notice what we've done here is everything else in this Fmoc system, all the carbons of that benzene ring, all the carbons of that benzene ring are sp2. They're all involved in resonance. They bridge through the bottom, but their flow is interrupted by this sp3 atom at the top. Now I turn to sp2.
Flow? Oh, the resonance sort of flow.
Yeah, so now I turn this middle ring into an aromatic ring as well, because
Okay.
it's got 6 pi electrons.
Yeah.
So I went from not having an aromatic ring to having an aromatic ring, and that's very, very, very stabilizing. So this is what you make. Then what this does almost immediately is it reacts with another equivalent. Basically, we're going to put that hydrogen right back on. So this nitrogen attacks there. Use a different color. And we just formed aromaticity, and now we break it again because it's aromatic, but it's not super aromatic. I attacked the wrong carbon. So we get this. And we're good. Like this is reasonably well behaved. The problem is this doesn't always happen, and this is kind of an equilibrium. This stuff forms stupid white insoluble concrete. So these Fmoc plaques, what you'll do is if you do an Fmoc deprotection, you'll get this white precipitate crashing out of the reaction if you try and dry it or purify it or any further. It stays nice and soluble in this 80-20 pyridine DMF solution, but as soon as you start trying to purify and change solvents, this white crap falls out and your molecule gets trapped in it and everything's kind of a disaster. So Fmoc is wonderful to take off. It's horrible to isolate. The other nice thing about it is it's UV active. So you can see the presence or absence of Fmoc by UV really easily, which gives you kind of a label to figure out how well things are going on and coupling or how well things are coming off. But this whole issue of being wonderful to take off but being horrible to isolate means that nobody uses Fmoc for solution phase synthesis. Solution phase synthesis is when you take your molecules, you mix them together in solvent, you make your peptide bond, you then isolate the molecule you made, you purify it, you put it back in, do more solution phase. And the reason it's really nightmare is because you get these plaques forming, your molecule gets trapped, your yields fall off, it's a pain in the ass. So, for solution work, CBZ and Bach are king. But Fmoc dominates the field. And that's because nobody does solution phase peptide chemistry if they can get away with it. And this is used in solid phase peptide synthesis. Yeah, okay, let's finish off talking about the the common carboxylic acid protecting groups, and then we can move on. Because if you're doing, again, if we're doing anything like this solution phase work, we need to protect one of the carboxylic acids. Otherwise, we need to avoid having two free carboxylic acids at any time. And so there are three here. And unsurprising to anybody at this point now, one will be base sensitive, one will be acid sensitive, one will be hydrogen sensitive. Because again, we're just not very creative. So acid sensitive. There are like tons and tons more. If you open up a book, you find millions. But they're mostly just derivatives of these guys. And there's not a lot of call to use other ones. I'll draw out the carboxylic acid. So we have the tert-butyl ester. Now, mechanistically, it behaves absolutely identical to the Bach that we saw. Let's take off. H plus. Same mechanism, except you don't decarboxylate. So I'm not going to draw it. The way you put it on use a bit of tert-butyl bromide and a little bit of silver and a bulky base. That's the general conditions. So you've seen silver bromine chemistry in the carbohydrate stuff, so unsurprising, silver's pulling the bromine off, which leaves you with the tert-butyl cation, which then gets trapped by the carboxylic acid. So I guess this needs to be protected, otherwise it'll react with this nitrogen, but let's just stick some sort of protection group on here. PG, I guess, it's not phosphorus. There are other conditions to put these on. You can look them up. If you need them, this will work. I'll accept that. That's pretty straightforward. And this is just, and we can abbreviate this. I'm just going to draw it over here, because there's nothing we love more than abbreviating things. Little t butyl for tert-butyl. Or you can draw it out, because I think it takes probably less pen strokes to draw it out than to abbreviate it, but we just like abbreviating things. Base sensitive. Is the methyl ester. So there's a couple ways you can take this off. You'll see either sodium hydroxide or lithium hydroxide. You'll see lithium hydroxide more often. Why? Lithium makes a stronger bond to oxygen than sodium does. And so the hydroxide is not quite as basic. So what we're doing here, a little bit more nucleophilic. And what we're doing here, strangely enough, is normally you would think, I don't know, normally I would think that I would attack the carbonyl of the ester with the hydroxide, generate a tetrahedral intermediate, collapse that down and kick out methanol, and that's not what happens. People have done studies on this, and it pisses me off because I don't want this to be the truth because it confuses me. This is unique to methyl esters, And it's because they're not very sterically hindered. You actually do a nucleophilic attack on the methyl group. The way they figured this out, this happens, is they have labeled the oxygen with carbon oxygen 18, and they can track where the oxygen 18 reacts with the carbon 13 that they label the methyl group with, and they find that you make an 18-13 bond. You don't see any of your hydroxide from oxygen 18 bound to the carbonyl. It is entirely bound to the methyl group. And so this must be the mechanism. It's doing a direct attack. It's a very, very clever use of labeled atoms to do this kind of chemistry. I just wish to attack the goddamn carbonyl group because that would be so much simpler, but it doesn't. Still, the problem with these is if your molecule is very sensitive to base in other places or sensitive to nucleophiles, you just threw in a really strong nucleophile. So the much more careful way of doing this, at least on paper, is to use lithium chloride. Lithium chloride is pathetic at doing anything. It needs to be completely anhydrous. If there's any water in there, it doesn't work. So you need to take your lithium chloride, and we call it fused lithium chloride. We basically take lithium chloride, we heat the crap out of it in a furnace at like 1,000 degrees Celsius, drives off all the water, you get just pure lithium chloride. Then you have, a week or two before it absorbs water again from the atmosphere. And then the chloride attacks the methyl group. Same way, exactly as above. It's much gentler. And methyl chloride, of course, is a gas. So we have this gentler way of deprotecting it. I think the reason you need to drive off all the water is because the water makes hydrogen bonds with the chloride, if not, and that attenuates its reactivity enough that it no longer reacts because it's pretty happy hydrogen bonded. So you need to make sure there's no water present. I guess that's what anhydrous means, but I just really want to emphasize that it needs to be dry. Actually, my favorite part about these things is the way to put them on. Because it uses my favorite reagent of all time, which is diazomethane. So that's diazomethane. It is CH2. It's one step away from being nitrogen gas. It's massively explosive. It's super toxic. I just really like the yellow color it makes. It's beautiful, and it's just very pretty. I think I really like toxins, apparently, and things that blow up. So this is the standard way of drawing it. So this is diazomethane. You make it. I'm not going to talk about how you make it. That's beyond the scope of this course. But you have to make it fresh because you can't ship it anywhere because it blows up. So you can't buy it. Anyways, you get. This is why it's inherently unstable. Because look, you just made a nitrogen-nitrogen triple bond, and that's the core of nitrogen gas. Now, diazomethane is not really basic. because it's this Zwitterion, like the negative and positive charges are both needed in there to stabilize each other. There's no way to get rid of them. There's no way to draw it with no charges. But though it's slightly basic enough to deprotonate carboxylic acids, but only carboxylic acids. So you can have a million functional groups in your molecule and it will react only with the carboxylic acids, which is really cool. So you get real selectivity here. Now you generate the O minus, you generate a CH3. It's neutral now, and it's attached to nitrogen, triple bonded to nitrogen. And what the second thing that's really cool about this, the second step of this reaction is so fast. That first deprotonation is kind of slow, but as soon as that happens, you're going to make nitrogen gas. So the methyl group has deprotonated the carboxylic acid. It's held in very close proximity and it snaps shut immediately to give you the carboxylic acid, the methyl ester, and nitrogen gas. And this, of course, is a gas. So what we've just done is we've taken something really, really dangerous and super toxic. We made it into like the most innocuous thing possible. Nitrogen gas is like we couldn't survive entirely on nitrogen gas because we need oxygen, but it's the dominant thing we're breathing at all times. Like it's perfectly safe, and methyl esters are perfectly safe. So I just love this dichotomy of extreme danger coming to just the most benign things ever with super selectivity. There are other ways you can put a methyl ester on, but they're more boring. Use methyl iodide in a base. You can use a Fischer esterification as we saw, so you keep the crap out of it with methanol and acid. Never recommend that when you have a peptide. This can be done at minus 20 degrees Celsius. So it's very, very, keep it cold. Nothing else happens. So we have this base sensitive group. We've seen the acid sensitive group. And then we have, unsurprisingly, the hydrogen sensitive one. Which is a benzyl ester, which shouldn't surprise anybody. Hydrogen, palladium on carbon. It's exactly the same reactivity we saw with the CBZ group. The way you put it on is exactly the same way you put, well, there's a bunch of ways. The most common way would be to use a base, normally a carbonate, and benzyl bromide. It's probably the dominant way to put it on. So this is how you put it on, how you take it off. It gives a bit more selectivity. So we have acid and base and hydrogen sensitive amine protecting groups. We have acid and base and hydrogen sensitive carboxylic acid protecting groups. Ideally, if you're working on a system, you don't want them to be sensitive to the same thing. So if you're building peptides by deprotecting amines like we saw, which is the way you should be doing it, and let's say you're using Boc on your amines to do that, then you don't want an acid sensitive protecting group on your carboxylic acid terminus because then they'll both come off at the same time. So if you're using acid on your amines, you probably want to use hydrogen on your carboxylic acids. If you're using base on your amines, you can use hydrogen on your carboxylic acids. You want to make sure that they're what we call orthogonal to each other. So what deprotects your acids doesn't deprotect your amines, and what deprotects your amines doesn't deprotect your acids. And you've got 3 options here, so pick 2. And it doesn't really matter what you use. Theoretically. Practically it matters a lot, but on paper, for the purpose of this course, it doesn't freaking matter. Okay. Now, let's say we're doing a solution phase chemistry synthesis. I want to talk about the strength of solution phase chemistry too. So let's say I'm making an peptide. Alanine, valine, glycine, phenylalanine, leucine. Okay, so I haven't indicated anything on a termini. What I will normally do, what I will always try and do in this class is I will try and indicate what is at the termini. Is when where is the N and where is the C terminus. If I hadn't done that, by default, the alanine is at the N terminus. The leucine, I always confuse leucine and lysine. The leucine is at C terminus. By default, that is the way it is. So let's say I wanted to build this molecule and I want to use a solution phase synthesis approach. How would I go about doing it?
But you want to use what?
I want to use this
Is-
solution. So I want to make this molecule, and I want to make this molecule using chemistry. How would I? This is so one of the assignment questions is basically build libraries of these things, design your strategy for doing it. Where do I guess we can do this retrosynthetically. You can do it synthetically too. I don't care.
So are we still doing this one amino acids by one? I mean,
Sorry?
are we still doing this one amino acids after the other?
Yeah, we can do it exactly. We can only connect one amino acid at a time. So let's say we're starting from each of the individual amino acids. So you have alanine, you have valine, you have glycine, you have phenylalanine, and you have leucine. That's what you've got. So you got like a kilogram of each of these raw amino acids on your shelf. You have any other reagents you need. What would be your strategy to put this thing together? So remember, each of these is an H2. None of these have interesting side chains. None of these have active side chains. We're not. Keep it simple right now. Right, so they're all. And this is actually the way that you'll see this written. Like what you'll actually see is something like ALA, OH, and H2. That means I have alanine, carboxylic acid, free, amine free. But since I'm using one-letter codes, I'm switching to this system.
N terminus and C terminus. So we start with alanine and try to protect the part that we want, and with the next amino acids, so we try to protect them, and I mean we try to, as it said, 2 by 2, and just protect and deprotect the functional group that we want to have an interaction with each other, and same as this. I mean, it's just
So which one would you do? So okay, so alanine, what would you protect, the amine or the carboxylic acid?
Carboxyl, amine,
Yeah,
because
so you
the
would take
carboxylic acid should
be free,
react.
right? Yeah, exactly. So let's say we take, so if we're thinking about all this, I'm just going to skip to the next slide. So we would take ALA, CO2H, NH2. We will protect that. Let's say, what do you want to protect it with?
Fmoc.
Bach, okay. I didn't talk a lot about, it's in the notes that are posted online. I didn't talk a lot about how to put these protecting groups on. You use Bach anhydride for this. Normally a weak base, imidazole. So we would have Bach and now I'll write this as Bach ALA OH. Okay, so that's your alanine. I skipped a slide. Okay. So now you protected your alanine. What's the next thing you want to do?
Third one should be the carboxylic group should be protected.
On which one? On which one?
And the V, what was the name of it?
On V, you want the carboxylic acid protected. Well,
Yeah,
okay. Because you don't want it to
this,
react with this one, right?
yeah,
So you want valine,
away.
NH2, OH, and you want to protect the carboxylic acid. How do you want to protect it?
Oh, again, the same as before. I have always this question, and you answered before, but this is necessary, right? Always protected, and
We need
yeah,
to protect this carboxylic acid. You're right.
yes,
No, you're absolutely right. How
yeah.
do you want to protect it?
With something that um,
So we had if we just pick from the three that we discussed, we had the methyl ester, the terbutyl ester, or the benzyl ester.
disaster. The way I'm sorry, I can't remember any other condition, but the condition sheet doesn't, I mean, make
Well, which
any
one do you want
trouble
to
for the
use? Do you want
bulk.
to use methyl, benzyl, or terbutyl?
Turbid.
I'm going to say no, you don't, because the way you take off terbutyl is the same way you take off Bach.
Yeah, the bulk, yeah.
So let's
This
not
is
do
what I
terbutyl.
mentioned.
Let's use either methyl or benzyl. Let's use the benzyl ester. So we just saw that you use base benzyl bromide, and we'll get NH2, valine, CO2, terbutyl. Okay, and then you can couple these two together, right?
Yeah.
Okay. So we would represent this like this. Sorry, not terbutyl. No, it's a CBZ group. Sorry, I'm having real trouble saying benzyl, just BN. There. So we would represent or I guess OBN. We'd represent it this way. I'll accept BN. I just want to be really specific here. So we've got Bach, Ala, Val, OBN. Now, I'm fine with that. What's your next step?
The problem is in V to G is not going to be yes, N terminus again, N terminus from G to is there any problem? Okay, to protect the acid from V group, and in order to be able to have it, yeah.
Okay.
And for the next amino acid, we need the amine group. So there's no need to protect amine group, just protect the carboxylic acid.
And there's no reason to make our life harder. So what we should probably do is take this glycine. If you need to look up the 3-letter codes and everything, just have a table that you have readily accessible to you. This course isn't about what is the structure of these amino acids. You're supposed to know that. So let's protect it using the same way. Let's just not, there's no reason not to use the same protecting group. Once you've gotten one protecting group strategy going for a sequence, stick with it. I'm just going to write OBN. Okay. And now you want to couple these two together, right?
Yes.
Okay. I now have a problem with this.
This is not it.
What's my problem?
And N to O. I mean,
Yeah. You've just
NTO.
epimerized your valine.
Oh, yeah.
Right? Because you've created an activated ester attached to your valine. You put it under the reaction conditions and you epimerize your valine. Now, that wasn't a problem initially with your alanine because you had a Fmoc group here, not an amide, but now we do. So your valine is now epimerized. Now, not fully. You might be able to get away with this, and I'm going to allow this because our sequence is short enough that, let's say, 10% of it epimerized. We can separate that out theoretically. It's not a huge deal. So let's just bracket that and note that this is a problem. The C with the crossover is with. I think we've lost something because we know, like I no longer know all the shorthand abbreviations. But, you know, they used to have tons of abbreviations for everything. And then when we all started typing, we all lost all those abbreviations, and now nobody understands any of them. But there's tons of ways to write stuff fast. Anyways, the if you want a hobby, you can learn shorthand. The epimerization is an issue that we're going to have here, and so it's just something to flag. It's not necessarily a huge deal with a really short sequence. Okay, let's go back to our sequence. And we just need a phenylalanine and a leucine. So we can do this two ways. We can add the phenylalanine next to the glycine. And in that case, we're not going to run any risk because glycine can't epimerize because glycine doesn't have a chiral center. It's just CH2, right? So we're not going to propagate this epimerization problem much further. What I'd suggest we can also do with the strength of this, but then what we run the risk of if we do that, if we add the phenylalanine next, we'll epimerize the phenylalanine when we add the final leucine. So what if instead of worrying about this, so we've already epimerized our valine a bit, what if we make this dipeptide, the phenylalanine leucine dipeptide, pre-make it, and then we can mix it with this trimer we've already made. And then the only thing we're going to be epimerizing is this glycine, and we can't epimerize that glycine because it's glycine. So we can avoid epimerizing any more centers by making phenylalanine leucine in advance. So let's just draw that out and just sketch that. So let's just remember we've got that. So if we're going to do this, I need to protect the N-terminus of phenylalanine. And just for the sake of argument, I'm going to protect this with it's benzoyl anhydride. CBZ anhydride, sorry. With a base, probably imidazole. And then I have my terminal leucine. Now, what I'm thinking about here is I need to protect the carboxylic acid. And ideally, I'd like to minimize the number of deprotection steps I need to do. And if I look at what I have on the other side of my peptide, I've got a Boc group. That comes off with acid. It would be nice if I can take off the two ends at the same time, because I only need to use one deprotection. This is acid sensitive, so let's take an acid sensitive group on this guy. So the way we did that was with the tert butyl bromide and the silver. Now I can couple these two together. So I got my phenylalanine leucine dipeptide. And then what I want to do is I want to deprotect this so I can couple it to the carboxylic acid on my glycine from my previous step. And I can do that using hydrogen and palladium on carbon. And so now I've liberated my amine. I have this terminus protected from this guy. I might want to, before I put that in a box, let's just deprotect it. So we'll deprotect the carboxylic acid. Boc, ala, valine, star for being epimerized, glycine, OH. So we have a free carboxylic acid, the nitrogen is protected. We've got a free amine, carboxylic acid is protected. So now I can stick the two things together. And now I run the risk, I would epimerize this glycine, but I can't epimerize this glycine because glycine is not epimerizable. And we just treat that with acid. So that would be to lay out the synthesis of this peptide from the building blocks. What we had to do was sequentially protect things with appropriate protecting groups, think about epimerization, and then go. Now, there's no way to avoid epimerization unless we build. So Rona has wanted us to start with the alanine over here because she has that, you'd think, no comment on this, but you'd think Persians might be able to think right to left, unlike us English speakers who always think left to right. So we're always biased to thinking going this way and reading this way. So I start with the left thing. But if she had embraced her Persian heritage, she could have started with the leucine and built the other way, and then we wouldn't have had to worry about epimerization because we would never have an activated ester. So if we want to build this linearly, that is the way we want to go. We want to go from O to C, not N to C to N, not N to C. But this is a perfectly appropriate synthesis, what we indicated here. This would generally work. We'd have a slight epimerization of the valine. We could really tune our conditions to try and minimize that. What you do is you keep your temperature short. You add in lots and lots of extra nucleophiles, so you try and make the attack of your amino acid faster than ring formation. And it's possible to do. You don't pre-make the activated ester. You make the activated ester in the presence of the amine already there. But I still think this is good. The other thing I want to point out is what we did was called a convergent synthesis. So don't make one amino acid at a time. That's really weird. You can make shorter oligopeptides and stick together, even with the problem of inevitably of some epimerization. This is almost always more efficient in solution phase because you're going to decrease the number of overall steps. What you want to make sure you're doing is you want to make sure that no amino acid goes through that many steps. The fewer steps any given amino acid goes through in the entire sequence, the better. And by making the phenylalanine leucine one in advance and then connecting it together, the alanine, the first amino acid, didn't need to add phenylalanine and then add leucine. It could add them as a single unit. So it decreased the number of total steps that alanine had to go through. That is going to increase your yield. It's a shorter linear sequence for the thing that has to go through the longest sequence. Minimizes what's called the longest linear sequence, which is total steps of any component. And that's what you always want to do. But we have this epimerization problem. So the advantage of a linear sequence going leucine first, then phenylalanine, then glycine, then valine and alanine, one by one by one, is you get none of that epimerization. In solution phase syntheses, you almost always want to do a convergent synthesis because the step count gets really long. But next class, we're going to start talking about solid phase peptide synthesis, and in that, you always do it linearly. Yeah, and so I guess we'll talk about that on Monday. In the meantime, you can really get started on all the assignment questions to do with amino acids, especially some of the background stuff, which says, hey, look up side chains and the different types of protecting groups for that. It's a good idea to have those available to you and written down because they're helpful for all the questions we need to synthesize things. So I kind of scaffolded the questions by saying, hey, look this stuff up so you have it available to you. I would do that. Yeah. I also I got the undergrads sent me their next step of their sort of outline of their talk. So the undergrads are not here today, but the grad students, I think you guys all owe me the next step of the paper. Maybe it's next week. I haven't checked.
I think the next deadline is first
Of December?
December, yeah.
Oh, okay, then you guys are fine for a while. The deadlines don't completely match because you guys
Yep.
get a bit more time. Okay. Carry on. Have a good rest of your day. Bye.